So today in AC electrical circuits, we're looking at lab number 11, parallel resonance. This exercise investigates the voltage relationship in a parallel resonant circuit. Of primary importance are the establishment of the resonant frequency and the quality factor, or Q, of the circuit with relation to the values of R, L, and C components. The reference sections refer to Shom's outlines of basic electricity, and we're looking at Chapter 21, Series and Parallel Resonance, and in particular we're looking for parallel resonance. So Chapter 21 is all about series and parallel resonance. And you can see we have a chapter on parallel resonance, and they talk about pure parallel LC circuits. Unfortunately, they don't have a section on LCR circuits. They do talk about practical parallel LC circuits in Figure 21-6. In Figure 21-7, they give us impedance and current response curves of practical parallel LC circuits at resonance. And they do talk about Q of the parallel circuit. They also have a nice section on bandwidth and power of resonant circuits. And Figure 21-9 talks about bandwidth of a tuned LC circuit. And Figure 21-10 shows us the resonant response curves for higher and lower Q values. Unfortunately, inductors are not 100% inductors. They do have a resistive element to them, so we have to be able to convert from a series to a parallel type circuit, and for this we need to reference our textbook, and we can see that we can convert R in series with XL to R in parallel with XL. So now XL becomes purely inductive, and it's in parallel with a resistor. And these are the formulas that we're going to be needing today. In the theory overview, we can see that a parallel resonant circuit consists of a resistor, a capacitor, and inductor in parallel, typically driven by a current source. At some frequency, the capacitive and inductive reactances will be of the same magnitude, and as they are 180 degrees in opposition, they will effectively nullify each other. This leaves the circuit purely resistive, the source seeing only the resistive element. And you can see they've given us a couple of formulas. So under equipment, today we're going to be using the circuit test SWF 7000, and we won't bother with its serial number. The oscilloscope TDS 1002, we won't bother with its serial number. We're going to use a ×10 oscilloscope probe, and it's made by Circuit Test, and it's model number OP-60, and I won't bother with its serial number. And the digital multimeter will be the Mastech MSM 9803, and I'm not going to bother with its serial number. Now under components, I've already gone ahead and measured my components to make sure that they are the correct ones. My 10 nanofarad is actually 13.45 nanofarads. My 10 millihenry inductor is 22.3 ohms. My 2.2 k ohm resistor is 2.177 k ohms. My 10 k ohm resistor is 9.88 k ohms. And my 100 k ohm resistor is 100.2 k ohms. So this is one of our circuit test OP-60 ×10 oscilloscope probes. As you can see, the wire is a little bit thinner than our ×1 probes that we've been using. The ×1 probe typically is under $10, whereas a ×10 probe like this would be somewhere in the $50 range. At one end here we have the BNC connector that we're all familiar with. At the other end we have our positive connection and our ground or 0 volt reference connection, and the 0 volts is connected through this fairly thin wire to a little alligator clip so it can clip onto ground planes and that kind of thing. On the positive tip of the probe, you can see that we can actually retract it, and it has like a little hook in there, so the hook can actually go around pieces of wire or around resistors. So typically it would just clip on there like so and just hang off, and it wouldn't fall off. And to disconnect it, you just retract it again and then take off whatever it's hooked to. Taking a close-up look, you can see that we have a slider switch on here. So if we move it all the way to the top, it's on ×1. And if we put it in the center, it's on reference, or it's shorted out to ground. And if we have it in the lower position, it says ×10. So on the ×1 position, the input resistance of the oscilloscope is about 1 megohm. And when you slide it down to the ×10, it makes the input impedance of the oscilloscope 10 times higher, so it becomes a 10 megohm input impedance. That way your oscilloscope doesn't load down your circuit. In the center here, there's a place for a small screwdriver. So typically what you'd do is you'd hook this up to a square wave generator and adjust it until your square wave looked exactly square. So you're actually adjusting the impedance of the probe. We're not going to bother with that today. We just need it on ×10 so it's a higher impedance for channel 2. So this is our schematic today, figure 11-1, and you can see we're going to have a voltage source rather than a current source. It's going to have an internal resistance of 50 ohms. So when you're working with resonant circuits, you have to account for all the resistance in the circuit. So the first resistance is the 50 ohms that's internal to the function generator. The next component we have is RS, and basically what it is a 100 k ohm resistor. So if we have a 100 k ohm resistor, basically our whole voltage based power supply is going to become a current source, because whatever we connect to the 100 k ohm resistor is going to be insignificant compared to the 100 k ohm resistor. So the 50 ohms internal to our voltage source is insignificant compared to the 100 k ohm resistor, so we can ignore the 50 ohm internal resistance. And then you can see we have a 2.2 k ohm resistor. Basically that's going to be insignificant compared to the 100 k ohm resistor. So you'll notice in step 2 of under procedure, it says the large value of RS associated with the voltage source will make it appear as a current source equal to approximately 10 volts peak to peak divided by the 100K, and that's equal to 100 microamps peak to peak, assuming the parallel branch impedance is much less than RS. So looking at this part of the circuit, it's now become a current source, and it's generating 100 microamps of current going into our parallel circuit. So we have RA, which is 2.2K. We have our inductor and its internal resistance. So we have a 10 millihenry inductor, and our coil resistance in the past it's been around 22 ohms. And that's in parallel with C, which is a 10 nanofarad capacitor. And then we're going to take our V parallel, or our output voltage, across the entire parallel circuit. So under schematic, you can see I have inductor in series and its internal resistance in series. So that's the 10 millihenry and the 22 ohm coil. And then we have the inductor in parallel and its internal resistance in parallel at resonance. Now it's very important that we use it at resonance. So we have R coil parallel in parallel with XL, and that's XL at resonance. So to transform R coil from series to parallel, we use R coil parallel is equal to the R of the coil squared plus XL, that's at resonance squared, divided by the resistance of the coil. And XL in parallel is equal to the resistance of the coil squared plus XL squared, now that's XL at resonance, divided by XL, which is also at resonance. So under procedure, step 1, this is a low Q circuit. We're going to use the figure 11.1 with RS as 100 k ohms, RA is 2.2 k ohms, L is 10 millihenries, and it has a coil resistance of 22 ohms, and C equals 10 nanofarad. Now we're to determine the theoretical resonance frequency and Q. You must convert the inductor's coil resistance to the parallel equivalent resistance, since this will affect the Q. We're to record the results in table 11-1, and based on these values determine the upper and lower frequencies defining the bandwidth F1 and F2. We're to record those in table 11-2. And it says since RS is so large we can ignore the effects of RG in the calculations, and RG is the internal resistance of the function generator. So I've given you the calculations that we need to perform. These are calculations for both circuits. This is with RS equal 100K, C equal 10 nanofarads, L equals 10 millihenries. Our coil, we'll assume everybody's is going to be the 22 ohms, and the applied voltage is going to be 10 volts peak to peak. So our frequency at resonance is 1 over 2 pi square root of LC. Now this is the simplified formula. It'll work fine for our case. So F at resonance is going to be 1 over, and I've put brackets in to indicate that we need to hold things together for order of operations. So we've got 2 times pi times the square root of 10 millihenry times 10 nanofarad. And it's important to keep those together when you're doing the square root function. And you can see the resonant frequency is going to be somewhere around 15.9 kilohertz. Now XC is 1 over 2 pi FC, so that's 1 over 2 pi times, and the frequency is the resonant frequency that we're interested in. So that's 15.915 K times the 10 nanofarads. So that works out to 1 k ohms at an angle of minus 90 degrees. XL is equal to 2 pi FL, which is equal to 2 pi times the resonant frequency of 15.9 kilohertz times the 10 millihenries, and that works out to 1 k ohm at an angle of plus 90 degrees. So you can see XC and XL are equal in magnitude and opposite in phase angle. We now have to convert the coil and XL to their parallel equivalents. So our coil becomes 22 ohms squared plus the 1 k ohm squared, which is XL. So we're still working at resonance frequency. So we divide the whole thing by 22. Notice the 22 at the bottom is not squared. So our coil in parallel is equal to 45.5 k ohms. And you can see that's almost insignificant compared to RA of 2.2 K, but when we get to RA of 10 K, it starts to be a factor. Converting XL for the parallel component, it's equal to the 22 ohms coil resistance squared plus the 1K, that was the resonance of XL, divided by 1K, and that equals pretty darn close to the 1K ohms that it was before. Now, completing the calculations for the low Q circuit of RA equals 2.2K ohms, we can see the total resistance of the circuit is equal to RA in parallel with R coil parallel component. So that becomes 2.2K times 45.5K divided by the 2.2K plus the 45.5K, which works out to 2.1K ohms. So you can see RT has gone from being the 2.2K ohm resistor to 2.1K ohm resistor due to the internal resistance of the inductor, R coil. So the Q of the circuit is going to be equal to RT divided by the XL parallel component. So that ends up being 2.1K divided by 1K. So we're looking for a Q of about 2.1. The bandwidth is equal to the resonant frequency divided by Q. So that's equal to 15.9K divided by 2.1. So we're looking for a bandwidth of about 7.6 kHz. The lower frequency, or half power point, is equal to the resonant frequency minus the bandwidth divided by 2. So that ends up being 15.9K minus 7.6K divided by 2. So the lower frequency should be 12.1 kilohertz. F2, the upper corner frequency, is equal to 15.9K, the resonant frequency, plus 7.6K divided by 2. So that works out to 19.7K. So going between 12K and about 20K should be a 7.6K range. So in table 11.1, I've filled in my resonant frequency, my Q, and F1 and F2. So under procedure, step number 2, we're going to build the circuit of figure 11.1 using RS, which is our source resistor of 100K ohms, RA of 2.2K ohms, our inductor will be 10 millihenries, and our capacitor is 10 nanofarads. Now once we've hooked the circuit up, remember we're going to check our oscilloscope to make sure the output of the generator is a 10 volt peak-to-peak sine wave at somewhere close to resonant frequency. Now it says place a times 10 probe across the parallel branch, and it says since RS is 100K ohms, the standard 1 megohm input impedance of the oscilloscope will not be enough to isolate it from the circuit. And then we're to make sure that the channel 2 probe is set to times 10, or else our measurement readings will be displayed inaccurately. So looking at my circuit, you can see that the red terminal that comes from the function generator and channel 1 of the oscilloscope goes to the input of my 100K ohm resistor RS. The other leg of RS goes to my 2.2K ohm resistor that goes back to the common of the function generator. In parallel with the 2.2K ohm resistor, I have my 10 nanofarad capacitor and my 10 millihenry inductor. And because they have shorter legs, I have a little jumper wire going back to the common of the function generator. Now channel 2 is my times 10 probe, and I've just hooked it up here to the other side of my 100K ohm resistor. So this is V parallel, or V out. So this is my oscilloscope. You can see I've set the frequency to about 13 kilohertz. And you can see I've got two waveforms on here. The clean waveform is my input waveform. The first thing you want to do is press the channel 2 menu button and make sure that your probe is on times 10. And then from the measure menu, channel 1 should display frequency. Channel 1 should be displaying peak-to-peak voltage. And channel 2 should be displaying peak-to-peak voltage. Now make sure that you have your amplitude on your function generator set so that channel 1 is displaying as 10 volts peak-to-peak. Channel 2 is V parallel, or the output voltage. So under procedure, step number 3, we're going to adjust the frequency in small amounts, up and down, until the maximum voltage is found. Now this can be calculated using the voltage divider rule, and it should come out to about 215 millivolts or less. Okay, this is going to be the experimental resonant frequency, and we want to record it in table 11.1, and we're to note the amplitude. So the smaller waveform is V parallel, or our output waveform. So I'm going to slowly increase the frequency. And as you can see, the waveform is getting larger, and it's getting closer and closer to being in phase with our applied voltage. That's because XC and XL cancel each other out, and you're just left with a purely resistive circuit. And we know that in a purely resistive circuit, the phase angle is 0 degrees. If I go past the resonant frequency, you can see that it becomes out of phase again, and the waveform becomes smaller. So we're to adjust it to the resonant frequency, in which case the waveform will be at its largest point, and it will be in phase. So you can see my resonant frequency is approximately 17 kilohertz. And you can see my channel 2 peak to peak is approximately 210 millivolts. So in table 11.1, I've recorded my resonant frequency as 17 kilohertz. And on table 11.2, I've recorded my resonant frequency as 17 kilohertz, and V parallel is 210 millivolts. So continuing on in procedure, step number 3, we're to sweep the frequency above and below the resonant frequency until the experimental F1 and F2 corner frequencies are found. And this will occur at a voltage amplitude of approximately 0.707 times the resonant voltage. These are the half power points, so these should occur somewhere around 152 millivolts. We're to record these frequencies in table 11.1, and then we're to determine and record the experimental Q based on the experimental resonant frequency F1 and F2. Now, since my V parallel is 210 millivolts, I'm going to take 0.707 times the 210 millivolts, and in my case it works out to 148.5 millivolts. So when my channel 2 voltage reaches 148.5 millivolts, I know I've reached F1 and F2. So to find F1, I'm going to decrease the frequency of the function generator until channel 2 reads somewhere around 148.5 millivolts. So I'm going to record F1 as being 12.4 kilohertz and the output voltage as being approximately 148 millivolts. Now I'm going to increase the frequency until channel 2 once again decreases to 148.5 millivolts on the other side of my input waveform. So I'm going to record 22.2 kilohertz. At 148 millivolts. So on table 11.2, I've recorded F1 as 12.4 kilohertz at 148 millivolts, and F2 is 22.2 kilohertz at 148 millivolts. So back on table 11.1, I've recorded F1 as 12.4 kilohertz, F2 is 22.2 kilohertz, and then I've calculated Q as being equal to the resonant frequency divided by the bandwidth. And remember, the bandwidth is F2 minus F1, so that becomes 17 kilohertz divided by 9.8 kilohertz, which works out to 1.74. So under procedure, step number 4, they're telling us to take the experimental frequencies of table 11.1 and put these in the top entries of table 11.2. Now we've already done that because we wanted to record those voltages. Now they're telling us to do this for all the frequencies in table 11.2 to measure and record the voltage across the parallel branch. So for the rest of table 11.2, they want to know what V parallel is at 1 kilohertz, 5 kilohertz, 8 kilohertz, 12, 20, 30, 50, and 100 kilohertz. So at 1 kilohertz, channel 2 is at approximately at 8 millivolts. So to get a clean line on channel 2, I had to go to the acquire menu and turn on averages. At 5 kilohertz, I'm at 36 millivolts. At 8 kilohertz, I'm at 64 millivolts. At 12 kilohertz, I'm at 126 millivolts. At 20 kilohertz, I'm at 164 millivolts. At 30 kilohertz, I'm at 88 millivolts. At 50 kilohertz, I'm at 42 millivolts. At 100 kilohertz, I'm at 22 millivolts. So on table 11.2, I've recorded V parallel for each of the requested frequencies. So under procedure, step number 5, it says based on the data from table 11.2, we're to plot the parallel branch voltage as a function of frequency on plot 11.1. We're to label the resultant plot as low Q. So for plot 11.1, where we're going to graph V parallel versus frequency, I've provided you with semi-log graph paper. So this is my plot 11.1. You can see on the horizontal axes, I've already pre-labeled it for you, and its frequency in kilohertz. Now this is called semi-log graph paper. So on the horizontal axes, we're actually using a logarithmic scale. So it goes from 1 kilohertz all the way up to 10 kilohertz, and as you get closer to 10 kilohertz, you can see the spacing gets smaller. And then it increases by 10, so next step is 20 kilohertz, 30 kilohertz, all the way up to 100 kilohertz. My vertical axis is voltage, and it's in millivolts peak to peak. And you can see I've already labeled it for you, so the major division is 100 millivolts, 200 millivolts, all the way up to 1,000 millivolts or 1 volt. I've tried to put my points in as close as possible to my measured values, and then I've tried to sketch in the line by hand, and I've labeled my resultant as low Q. We're now moving on to the high Q circuit. So under procedure, step number 6, it says for the high Q circuit, change RA to 10K ohms. Remember, RA was 2.2K ohms. Now we're to repeat steps 1 through 5, and we're to record our results on tables 11.3 and 11.4. Now we have a note here that the maximum voltage should be about 909 millivolts. That's taking the voltage divider rule and taking the 10K over 110K times our input voltage of 10 volts peak to peak. So 0.707 of the 909 millivolts will give us F1 and F2, and that should be somewhere around 642 millivolts or less. So the calculations for the high Q circuit, where RA equals 10K ohms, the first thing we're going to find out is what the total resistance is, and that's equal to RA in parallel with our coil parallel equivalent. And that's 10K times 45.5K divided by 10K plus 45.5K, and that works out to 8.2K ohms. So you can see if we just considered RA, it was 10K, but when we start considering that 22 ohms of the coil and take its parallel equivalent, it knocks our resistance down from 10K to 8.2K, which will affect the Q of the circuit. So the Q of the circuit is calculated as RT over XL, parallel equivalent, which is 8.2K divided by 1K, and that works out to a Q of 8.2. So our bandwidth is equal to our frequency at resonance divided by Q, which is 15.9K divided by 8.2. So we're looking for a bandwidth of 1.94K. So we can see changing RA from 2.2 to 10K changes our bandwidth from 7.6K to 1.94K. Our first corner frequency for F1 is frequency at resonance minus the bandwidth divided by 2. So that's equal to 15.9K minus 1.9K divided by 2, and that's equal to 14.95K. Our upper corner frequency, or F2, is equal to the resonant frequency plus the bandwidth divided by 2, which is 15.9K plus 1.9K divided by 2, which works out to 16.89K. So in table 11.3, I've filled in my frequency at resonance. It's the same as before. It's still 15.915 Hertz. Remember, it was the resistor that changed. The inductor and capacitor stayed the same. My Q is now 8.2. My first corner frequency, or F1, should be 14.95 kHz. And my upper frequency, F2, should be 16.89 kHz. So this is now my circuit, and I've swapped out RA that was 2.2 k ohms. It's now brown, black, orange, so that's a 10 k ohm resistor. Remember, you're switching out RA and not RS. RS still has to be the 100 k ohm resistor. So my first step is going to be to adjust the frequency in small amounts until we find the resonant frequency. And the resonant frequency is when channel 2 is at its maximum, and you'll notice it's also going to be in phase. So when we have it in phase, XC and XL cancel each other out, leaving just a resistive circuit. So it looks like at 16.6 kilohertz is my resonant frequency. And at resonance, it looks like I'm at about 648 millivolts. So on table 11.3, I've recorded my resonant frequency as 16.6 kilohertz. And in table 11.4, I've also recorded V parallel as 648 millivolts. And it doesn't hurt for you to put in comments on your lab pages so that when you come back a month or two from now, you know that V parallel was actually volts in peak to peak. Now please note that in the procedure, we said the maximum was going to be 909 millivolts or less. And our maximum V parallel was 648 millivolts, which is less than the 909 millivolts maximum that was possible. So to find F1 and F2, we have to take 0.707 of our measured max for our circuit, which was 648. So F1 and F2 should be somewhere around 458 millivolts. So starting from the resonant frequency, I'm going to decrease the frequency on my function generator until channel 2 says somewhere around 458 millivolts. So at around 456 millivolts, you can see my frequency is 15 kilohertz. Now I'm going to increase my frequency and go past resonance until once again my channel 2 reads 458 millivolts. So at 456 millivolts, you can see my frequency is about 18.2 kilohertz. So in table 11.3, I've recorded my resonant frequency as 16.6 kilohertz. F1, which is the lower frequency, is 15 kilohertz. F2 is the upper frequency is 8.2 kilohertz. Then calculating Q as being equal to the resonant frequency divided by the bandwidth, and that's equal to 16.6 kilohertz divided by 18.2 kilohertz minus 15 kilohertz, and that works out to 5.2. So now I'm going to do the rest of the frequencies in the chart. So at 1 kilohertz, channel 2 is at 8 millivolts. At 5 kilohertz, channel 2 is at 37.6 millivolts. At 8 kilohertz, channel 2 is at 72 millivolts. At 12 kilohertz, channel 2 is at 184 millivolts. At 20 kilohertz, channel 2 is at 284 millivolts. At 30 kilohertz, channel 2 is at 112 millivolts. At 50 kilohertz, channel 2 is at 68 millivolts. At 100 kilohertz, channel 2 is at 44 millivolts. So these are my results on table 11.4. So moving on to procedure step number 7, it says based on the data from table 11.4, plot the parallel branch voltage as a function of frequency on plot 11.1 and label the resultant plot as high Q. So in plot 11.1, I've tried to put my points in as close as possible to my measured values, and I've sketched my line in, and I've labeled it as high Q. On the last page of the lab, I have 4 questions for you to answer based on your calculations and observations of the lab. So when you come down to question number 4, how would you account for the V parallel at FR in table 11.4 being much smaller than the maximum described under procedure 6? You may have noticed that under procedure step number 6, where RA was 10k ohms, we said the maximum voltage should be about 909 millivolts. And you'll notice our actual maximum at resonance was 648 millivolts. So I want to explain where the difference came from. So to find the maximum V parallel voltage, all I did was say that XL and XC are going to be equal, so they cancel each other out. So you should be left with a voltage divider situation where we have the 10K over 110K times the 10 volts applied, and that should be equal to somewhere around 900 millivolts. We have to remember that there's a DC resistance to the coil. And when we did the calculation to find out what the parallel conversion of that DC resistance was, it was 45.5k ohms. So to come up with a more accurate voltage divider calculation, we have to take the 10k in parallel with the 45.5k, and that brings our RA value down to about 8.2k. So V parallel is equal to 8.2k over 108.2k times the 10 volts. And that works out to 758 millivolts, which is a lot closer to our actual reading of 648 millivolts. You'll note under procedure step 3, we expected the maximum voltage to be about 215 millivolts or less. So when we took the 2.2k and divided it by the 102.2k times the applied 10 volts peak to peak, it came out to 215 millivolts. When we compare the 2.2k to the 45.5k, we can see that the 45.5k is so much larger than the 2.2k that it didn't make a major difference when we did our pre-lab calculation. So to sum up your answer for question number 4, you could say something like, under procedure 6, where we thought the maximum voltage should be about 909 millivolts, it did not account for the DC resistance of the inductor coil, which needs to be converted to a parallel equivalent and then has to be added in parallel with the 10k ohm resistor to come up with the total DC resistance of the circuit. When you've completed your lab, show it to your instructor so that they can initial it to indicate that it is complete.